afternoon, everybody. I have your homeworks back. I recorded everything, all the homeworks. I didn't put checks on them. But if you look on Canvas, it'll show your homework grade. Okay? So if you have any question about whether there was some mix-up, you turned something in and whatever, then come talk to me. But it's on there. So there'll only be one homework grade for the entire semester. Okay? What I'm going to do is every time I collect the homework, I have a separate Excel spreadsheet that I keep track of the homework, like who turns in what. And as I've said before, as long as you turn in a majority of the homeworks, and I'm not going to set a number, it's not like 9 out of 10 or 3 out of 5. Don't turn in like less than half or something like that. You'll get the full homework grade. Okay? So your homework grade is reflected right there. For those of you that didn't turn in the first homework, the grade's going to start out low, and then as soon as you turn in the second one, it'll go up very quickly. So don't worry too much about the homework grade, especially until the end of the semester. If you feel like it's not reflective of your performance, then you can come talk to me at that point. Just turn in a majority of the homeworks and you'll get the full credit there. The main objective, again, is the quizzes and the exams. Any questions on that? Because I know people always get really dicey about the homework grade. Okay. So take yours back and then keep passing. So what did we do last time? So last time we went over a number of examples that were really more practical in nature, right? They were discussing how we can solve problems that are bigger, circuits that are bigger. And so what we saw was that we've learned some skills that that we can use, right? So what we saw was that the way we're going to tackle problems, at least in this chapter, is going to be to take large circuits, to collapse them down, right, using parallel and series combinations of sources and resistors. Solve the basic circuit, which hopefully we know how to handle, whether that's a single loop or a single node pair or some kind of voltage or current divider, okay, which in the end are single node pairs. And then once we have a value for that basic circuit, whether it's current or voltage, then we can start expanding it back out, again using combination of voltage and current dividers. It's a process that I think is probably, like we've been doing, best expressed by example. We also, last time, began talking about one last different way of, and this is not necessarily combining resistors together, but finding an equivalent for resistors, right? And that was called the Y to delta, delta to Y equivalency or conversion, whatever word you want to use. And what we saw was that we can take a configuration that looks like this, okay, and turn it into a configuration that looks like that, where these points correspond to these points, right? So these are, it's an equivalency for a simple network of resistors with 3 nodes each, or 3 terminals, okay, because I guess technically the Y connection has a 4th node that's in the center, right? So that node is not reflected, is not one of the terminals that we're concerned with when it comes to the equivalence. So I think last time what we did was we introduced the Y to delta, and we actually talked about when it would come in handy. So if you remember, what we showed was a circuit that I think looked something like this. Okay, it looks something like that. And so what we saw was that the way that this was configured, we didn't really have too many options for solving, okay? And the reason for that is none of these resistors are in parallel or series, which limits what we can do, given the methods that we've learned so far. But the Y to delta conversion helps us because what we can do is replace this with this. And now those go away. Okay? And so what you can see is after we do the conversion, we end up with these two resistors being in series, these two resistors being in series, then the two paths being parallel, and then in series, and you could actually boil the whole thing down to a signal. The only thing that we didn't do last time, this is where we stopped, is we didn't talk about explicitly what are the values of the resistors, because they're not going to be the same. The resistors that were here, which we were calling RAB, RBC, and RCA, right? Those are not the same value of resistors that will be what we call RA, RB, and RC. But it's just pretty simple formula. So that'll be something when it comes to quiz and exam time. That'll be on your cheat sheets that you use. Okay. So let's start putting those equations up. Are there any questions? I also fixed your quizzes. So if you go through and take a look at your quiz grade, you should have the 2 points for that fifth problem, regardless of what you put down. Some of you, either by being able to interpret what I meant by the problem or by guessing, had the right answer anyway. So if you had the right answer, then your grade would stay the same. I didn't just give 2 extra points to anybody. So if you already had the points for that fifth question, then your grade would stay the same. All right. And I also sent out an email with a link to the paper notes that we're doing, which, I mean, at this point, really, I'm just rewriting it because it assists, it helps in the explaining process, and also to slow things down. Because if I just talk about the notes as they're up on the screen, and things go pretty quickly. So I don't think they're necessarily any better than the notes that are already available. So use them if you want, or just use these that are available to us. The last thing we talked about, or not the last thing, one of the other things we talked about last time, which I could ask about for a second, was combining sources together. So can anybody explain to me what the rules are for combining together current sources? So there's 2 different cases that we have to be concerned about, right? We have to be concerned about series combos of current sources and parallel. So if you remember, for both the voltage and the current sources, there was only one way we could combine them, right? There was one of the, because we had the matrix, the 2x2 matrix. One of the 2 ways for each one of the sources was a no-go, meaning that there was something either mathematically or physically that prevented that combination from being viable. So which one for the current source was the viable one? The parallel or the series combo?
Parallel.
Yeah, the parallel combo works. So we can combine current sources in parallel. And the reason why it works is because KCL can still apply, right? The 2 currents go into the node, they sum together, you have IA plus IB going out. It doesn't work for series because, right, then KCL would essentially be, unless the 2 current sources had the exact same value, they would essentially, it would be negating KCL. So I guess technically if you got a problem where you had 2 current sources in series with the exact same value, then really the equivalency, you could just lump them together and just treat them like they were synced. But I wouldn't give a problem like that, and it wouldn't come up in a physical design because that wouldn't make any sense. And then so for the voltage sources, it's the opposite, right? So the series combos work, okay, and they get summed together. The parallel don't. And this is something that's a little bit more, I don't want to say dangerous, but it's a little bit more valid to discuss because you can actually hook up something like this with the equipment that we have in the lab. And so what you end up with is what we call the low impedance path or low impedance loop, where the two sources essentially will be fighting against each other, and there'll be very large current transients between the two of them, fighting over what the voltage is between each other. Anyway, you won't see that. You shouldn't see that. Okay, so let's go to where we left off, which was right. Okay, so how do we So how do we define the transformation? There's really two different cases. So case number one is for when all three resistances are equal. And we call this the balanced case. Okay, we normally can call, we would call that a balanced load. And so when they're all the same, that means that RA would be equal to RB would be equal to RC. And we could really give that a single variable name, which we'll call RY. And it would also mean that RAB would equal RBC would equal RCA, and we could call that the R delta. Okay. And so how do these relate to one another? Essentially, RY is equal to 1/3 of R delta. So if you're combining, if you're converting between balanced delta and balanced Y, well, if one's balanced, the other one will be balanced. If you have a balanced delta, the resulting Y will be balanced. You just divide that, or multiply that. So that's easy. Okay, now what about case number two? Okay, and this would be, and I think I can simply just write unbalanced, because now we know what that term means. And this one is a little bit more, requires more space. So we have RA is equal to okay, and I'm just going to call this right here, these three values summed together. I'm going to call this R A, that's an A, B, C, delta. Okay, so that's just the sum of all of the three written together, because they're going to be using the other equation. And then RB is equal to RAB, RBC over RABC delta, and then RC is going to be equal to RABC times RCA over RABC delta. Okay, so you can see that shows up right here. It also shows up right here. So you don't have to memorize these, but if you were, at least if you want to become familiar with the form, you could see, right, what you end up with is the two resistors that are adjacent to the node multiplied by each other over the sum of all three of them together, right? RCA, RAB, those are the two adjacent to A, RAB, RBC, two adjacent to B, etc. Okay, now the other form is, so RAB, this is going in the other direction, is going to be RA, RB plus RB, RC plus RC, RA over RB. And so we'll give this a name also, the numerator right here. We'll call it R, A, B, C, Y. And so RBC is equal to R, A, B, C, Y over RC. And RCA is equal to so you see those kind of reflected. So, that's it for that. Next topic. So this is section 2.8, which is circuits with dependent sources. Today's the 22nd or 21st?
21st.
All right. So there's 4 different types that we have to talk about, and I think if you remember, I discussed these briefly before. So what we have is 4 different combos. All right, we can have, well, let me ask you. So what are the two, I mean, hopefully this is going to be a no-brainer. What are the 2 different types of sources, right? Voltage. Okay, good. So we got voltage, and we got current. And, you know, I'm not even, this is too easy of a question, right? They're obviously going to be dependent on either voltages or currents, okay? Does anybody remember what the name was that we used for these different combos? Yeah.
Voltage dependent voltage source.
Yeah, voltage controlled. I mean, you hear them sometimes say voltage dependent, but usually they use the acronym. So for this one, this would be a voltage controlled voltage source, VCVS. This will be a voltage, sorry, I'm reading my table wrong. This would be a current controlled voltage source. This would be a voltage controlled current source. And this would be a current controlled current source. Okay. So that one right stands for voltage controlled current source. Okay, so you know what those are. Now we got to start talking about how to deal with them. The example here, all it really illustrates is how to do something that you pretty much know how to do, but in a different way. So we've been used to using KVL, KCL, Ohm's law, etc. Plugging in constants for the parameters, right? The resistors were constant, a number. The voltage sources were constant, a number. The only difference in dealing with sources, dependent sources, is that you use the same equations, but you fill in an equation within the equation. So KVL now, instead of having 5 volts, will have 3 times whatever, you know, it is. So let's take a look at example 227. All right, and this is a circuit with a dependent voltage source. And more specifically, not that this really affects how we do it too much, it is a current controlled voltage source, so CCVS. All right, so the circuit looks like this. We have a 12 volt source, we have a resistor, we have a dependent source, and we have another resistor. Okay, so this is 3,000 ohms, and this over here is 5 kilo ohms. And the source, which I guess they give it a name, they call it VA, is equal to 2,000 times I1, where I1 is the loop current that's running through this whole thing. And so first step, like any problem, is we label everything. That'll help us along. So the only things we really have to label, the current's already labeled, both these voltages are already labeled. I can give this a name, I'll call it VS. Okay, we need to label the voltage across here, so we'll call that V5K. Make sure to give it polarity. We'll also give this one, we'll call it V3K. And you can see, right, that we, as usual, have set the voltage across the resistors to coincide with the passive sign convention. Okay, so next step, what's the next step? Right, for most of these problems, the general process is write down the math and then solve. Honestly, and I think that getting the right equation is normally, are you raising your hand or just, no, okay. So normally getting the equation is the harder part. So our choices, Ohm's law, KCL, KVL, Kelvin's theorem, which one do you think is best here? We normally want to start with an equation that expresses, that includes as many of the variables and constants as possible. So which one do you think would do that? Say what? Ohm's law is a good option, but remember we wanted to try to get, so Ohm's law does encompass all the variables. Unfortunately, it encompasses all the variables in separate equations. So we want to try to encompass all of them in one equation. KVL, right? So, KVL, which hopefully now is old hat, what is that going to be? Can someone call that out for me? Let's assume that VS is positive, so we'll use that reference polarity. Well, we know the first term is going to be VS. So for KVL, again, just all the voltages in any given loop sum to 0. So we know it's going to be some different combination of VS, V3K, VA, and V5K. Normally the only part that's tricky is just making sure you get the polarity. Which polarities coincide or agree or reinforce VS? Well, no, those are opposing, right? Because if you continue out in a circle, you have minus plus, then you have plus minus, and you have plus minus. So the only one that reinforces it is this one. So we can write those two together if it makes it easier. And then now subtract out V3K and subtract out V5K. And that should equal 0. Okay, now we're going to do a substitution. When we have single loop circuits, what is the variable that we need to come up with in order to quote-unquote solve it? The current, right? Because that's the one value that relates everything together. For single node pairs, we need to come up with the terminal voltage across those two. Once we have that, then everything else falls into place. So, when we say put the equation in terms required to solve, you know, we would put a note here for a single loop. The current is the key value. Right, that's the one that we're trying to do. So we want to make substitutions that put as many of these in terms of current as possible, and the main option there is going to be on. So we have 12 volts, and we have a substitution for VA that also puts it in terms of I. So that'll be plus 2,000 I1. Then for both V3K and V5K, I can combine them together. It'll be 3,000 plus 5,000 times I1 equals 0. Anyway, to make a long story short, you can see where this is going. You can add these different values together. And when we solve, we're simply going to have, in the end, I1 is equal to, so all three of these together will have a negative 8,000 plus a 2,000, so negative 6,000. So we'll have 12 volts over 6,000 ohms. Right, because we'll move that to the other side of the equation. And so what does that give us? Gives us 2 milliamps. I didn't look at the numbers for a second. And then now we can also right, that'd be an easy one. All we have to do is multiply our 2 milliamps by our 5,000 ohms, and so that would give us a 10 volt difference plus that. So this is not much different than solving circuits with constants. The only real difference is that term. Like this. Now this problem would probably be a little bit more difficult / interesting if it were a voltage dependent voltage source. Because we're solving for I1, and this kind of just worked itself out because when we did the substitution for Ohm's law, we had this in terms of current. If it was a voltage-dependent voltage source, then we would have had another voltage, and you'd have to do a second substitution to kind of finagle the numbers in the right way. Okay, so that's what, well, that's not really what this problem is, this example is getting at, but it's another good example. And I'll talk for a second about why this is actually so relevant practically. So this one asks us to find the ratio of V out over V in. And the circuit looks like this. We have two decoupled circuits electrically. So we're going to draw two circuits side by side. But what you're going to see is that the link between them is through the dependent source. So this is R1, this is R2, this is RF. This we're going to call V out, and right, we're going to call this the input stage, and this the output stage. Now, why is this a good practical example? Because this circuit may be used to model amplifiers. So we're going to talk about amplifiers this semester. We'll talk about amplifiers even more for those of you who have me for electronics, or anyone for electronics at some point down the line. But this can describe how an amplifier works, or more accurately, it can model how an amplifier works. Okay, so this, there's a couple of values I didn't label yet. So this they call V3. Okay, and the value here is GM times V3, where the GM is a constant. It's the gain for this amplifier. And so I guess I called this IX, and for the sake of argument, I'll go ahead and give this a name, and we'll call this I. Okay, so all the values are labeled. We really want to be thorough. I could call this VR1, and I think that's all. So, how are we going to solve something like this? This is another one. As the problems become bigger and a little bit more complex, right, the path moving forward is not always going to be 100% crystal clear. So I find an exercise that works really well is to, well, I mean, I can't really write this down because it's so different from time to time, but think about this like critically. You know that what you're looking for is a ratio of V out to V in, right? So you want equations that obviously include V out and one that includes V in. So what we can do is we can write down a whole bunch of our options and see what more than likely you're going to have to combine multiple equations together into. So what I'm going to put down here for step number 2 is I'm going to say write out potential equations. Okay, so let's write out some of those that we know. For the left-hand side,
KCL is not going to be very interesting, right, because it's a single loop. But KVL would be pretty interesting. So we could say that V in minus VR1 minus V3 equals 0. And we could also write out Ohm's law, right? We could say V3 equals I in times R2. There's some other ones that we could write out, but probably not going to be. We know there's a V3 over here, so probably not going to be too useful. So let's start with these two for the left-hand side. Now, what about for the right-hand side? Is KVL going to be very interesting? Not really, because we don't, right, for a single node pair, they both have the same voltage. So, and KCL actually is not going to be very interesting because it's a single loop, right? This is both a single node pair and a single loop, right? That can occur. So, if you only have two elements. So the only thing that really makes any sense is Ohm's law. So we can say V out equals equals IX times RL. And now is where hopefully you can start recognizing some substitutions that you can make right off the bat. We know that this is the opposite of this. So I could actually rewrite that as this is going to be negative GM V3 times RL. Right. Okay? With this, well, because it's opposite direction. Opposite direction. Okay. So there's only really these three equations that are going to make sense. So what we can see right off the bat is that if we're trying to get V out and Vn together, we can use a combo of this equation and this equation. So we put them together to combine, well, it's not the best word, to derive equation with V out and V in. And so what would it look like when we put those two equations together? How are we going to combine them? What's the key to combining them? V3, right? Because that's the only variable that they both share. So what I'm going to do is there's two different ways of doing it. We could solve the left-hand side for V3 substituted in, or solve the right-hand side. I'm just going to solve the right-hand side one. So what I'm going to do is I'm going to write out, I'm going to say we have Vn minus VR1 minus, and now in place of V3, I'm going to solve for V3 over here. So what is V3, just real quickly doing it in our head, what is that going to give us? V3 is going to be equal to negative V out divided by GM over RL, right? Negative V out divided by GM times RL equals 0. And this right here is V out equation solved for V. And then now we have something that's in terms of both V out and V in. So the next step would be to solve the equation for V out over V in, or try to another way of saying it is to put it in that form. So the first thing I would do is I would move the V out to the other side, because then we can divide by V in, and we'll kind of be on the right path. It's not going to give us exactly what we need, but there's going to be a couple of intermediate steps. All right, so what that gives us is we have V out Okay, so where did we get this from? Right? So the first thing is that both of these minuses, right, will combine together to be pluses, right, because they'll cancel each other out, which means that when we move this over to the other side, the coefficient will be negative, so we have negative 1 over RLGM times V out equals, and then the left-hand side stays the same. Okay, and now what we'll do is we'll divide by V1, or we'll divide by V in on both sides. And I'll take this and I'll move it over to the other side. So what that leaves us with is V out over V in equals negative RLGM, right, because I moved that over to the other side, times 1 minus VR1 over V in. Okay, so the only problem with this equation is, right, we still have a V in. So if we're trying to calculate V out over V in, we don't want V in to be part of that equation. So what other substitutions can we do? And for this, we're going to need a picture. So what other substitutions can we do to get rid of this? All right, so the easiest thing would be to make some sort of a substitution for VR1, right? If we could get something that had V in it, and hopefully it would cancel out, and that would be good for us. So, right, we know that VR1 is equal to R1, or I in times R1. Now, furthermore, what is I in? I in is V1 divided by both of these resistors added together. So I'm just writing down a whole bunch of stuff I know. I in is equal to V in over R1 plus R2. So I can stick this in here. And what does that give me? That tells me that VR1 is equal to V in times R1 over R1 plus R2. And that equation should look familiar, right? Because it's our voltage divider. And so what you'll see is that we got the desired effect. Because when we plug this guy in here, right, the V-ins will end up canceling out. So what we'll have is V out over V in equals negative RL times GM 1 minus Vn over Vn, I'll just go ahead and put that down there, times R1 plus R2. Okay, so is this right? So we carry that down. You can't see everything. So we carry that down. The 1 stays. And now for this, I'm going to substitute in that right there. So we have Vn over Vn, R1. Okay, good. So these go away. And we have this. And so that's a nice equation that puts the gain of the whole thing in terms of just the resistances and the GM value, which is called the transconductance for the resistor. Now that's not necessarily the nicest looking form. If I were going to write this out, now, this is the correct answer. So if you got this on the quiz, that would be good enough. But since we're going through all this trouble, might as well try to be thorough. So, right, what we would try to do is carry out the denominator on both sides, or for both of these terms. So what you would have is, leave the GM over here, and we'll pull the RL in a second. So what that would give us is R1 over R1 plus R2 minus R1 plus R2 over R1 plus R2. So these two would cancel out right here. These are R1s because you subtract them from each other. And I think I can barely fit the answer in. Equals, the last thing you would have is GM, R2, RL over R1 plus R2. Now, problem is I lost the minus sign. Because the answer is supposed to be here. All right, so I switched here. I switched the R2 into 1, and that's what got rid of the negative. All right, so let's go through this once. This is a good exercise. When you come up with an answer, some types of problems, which is actually a pretty common one for quizzes, they'll actually tell you the answer, and they'll ask you to derive it. And then that's probably one of the most frustrating types, because then you end up with one little piece off, and you're sitting there kicking yourself. Okay, so let's take a look through this step by step, and hopefully we can pick out the piece where
I think it might just be the last. Like,
is it the last step?
Your very last step.
So what is it then?
See where you subtract R1 on the numerator?
Mm-hmm.
That would make that R2 negative, right?
Exactly. There you go. Sometimes the answer is easier than you think. All right. So that's the answer. Okay, so let's take a 2-second breather here, because we're ready to go over another example. Yeah, we'll take a 2-minute break. It's 1:22 now, and then we'll start again. And we'll do example 226. So while we take the break, though, we can take care of a couple of housekeeping things. So where do we stand as far as quizzes go? Our next quiz is going to be on not this upcoming Monday, but the one after that. So it's going to be on October 3rd. All right, that's going to be quiz number 2. It's looking like we're going to be done with chapter number 2. We can see how far. We have 2 more examples. 2, and then we're in chapter 3. So we're probably going to finish chapter 2 today. So what we'll do is we'll go ahead and set the due date for chapter 2 homework as the day of the quiz. All right? So October 3rd, quiz number 2, as well as homework number 2. Now, you will have a cheat sheet. So it'll be, it's actually 2 or 3 sheets that are stapled together, and it essentially is just copy and pasted from the book all the major equations. Telegin's theorem, KVL, KCL, stuff like the delta to y conversion. And honestly, if there's ever an equation that you don't have, if you raise your hand during the test and ask me to write it on the board 9 out of 10 times, I have no problem with that, because again, I'm really not concerned with you memorizing stuff. There's a few exceptions depending on how the problem is formulated, but yeah. That being said, you know, for the exams, not necessarily the quizzes, but for the exams, sometimes I do ask short answer questions. Now, those could be ones that require not necessarily memorization, but kind of in-depth knowledge of what's going on. Like, for example, and I kind of use this one already for the quiz, you know, what is KVL derived from? And then having some inherent understanding of the relationship between Telegin's theorem and KVL. And so, if you want, what I'll do is I'll try to email out a copy of the cheat sheet to you guys. That way you'll have some sort of clue what it is that you need. All right. So we'll go over one example, which is 226, that uses the delta to y conversion. So I think that'll be something different than 228. And I think you can take a look at that on your own. So this 226 will be the last example that we're going to do in this chapter. I haven't gotten any homework questions yet for this entire semester. I do encourage you, if you have homework questions, I mean, you're always more than welcome to come by my office hours. But it's also helpful to ask it in class, because a lot of times, for every student that has a question about a homework problem, there's another 5 or 6 that have that same question for them to ask. So, as we get closer to the homework number 2 due date, I encourage you to bring any questions. Okay, so example 226. So really, it's just solve for IS. Okay, so .12 volts here, and then it's 12. Let's see. I think 4. So 12, 4, 18. 9 kilo ohms and 4. All right, and IS is the source current. Okay. So, one thing that we haven't really discussed is a different way to label things. And so, we don't necessarily have to label every single voltage and every single current if we use consistent naming of the nodes themselves, right? So, if I name the node, so I'll name this A, I'll name this B, I'll name this C, and lastly D. I don't really have to name anything else, right? Because I can refer to things pretty easily. I could say, I know that this is voltage AD, and the polarity is automatically indicated by the order of the letters. VBA would be the opposite polarity. We know that this is voltage VD. We could also call this current IBD. Anyway, so you see what I'm talking about. You can, for larger circuits, if you just label all the nodes, it makes it easier. Okay, so second thing we're going to do is pretty sure I just spelled that word wrong, but so are there any potential parallel and series combinations? Yes, no, maybe? Right, for series combinations, we're looking for two resistors that share a common node, but nothing else is adjacent to that. There's not even really any node in here with only two connections, so that throws that out the window. And then you can see there's no parallel, right? Anyways, it's not. So, but what do we have? I mean, I'll tell you, pretty much any time, at least in this chapter, before we get to nodal and mesh analysis, if you don't find any parallel or series combos, that should just be a huge hint that you have to use a delta to Y transformation, because that's the only other way you know how to do it. So unless it's an unsolvable problem, which I'm going to give you, you're going to have to use that. Okay, so both of these are delta configurations. Most times when you do problems like this, you don't need to convert both, right? Converting one of them will do the trick.
Did you also say that those are Y configurations going?
Yeah, I see what you're saying, using this right here. You could,
That's what I saw at first.
yeah, I'm not sure if it would help the circuit though. Let's redraw it. I'm not going to go through the whole problem. I'm just going to redraw it with that in there. So this would be the neutral or the middle node. So what you would end up with, something that looks like this. So A, B, and D. So what you have is
That's if you can from the Y to the
Yeah, because if you take a look at this right here, right, the Y would be these three resistors, okay? You would still have, and if I label these nodes, so node C will go away, so you'd be left with A, B, and D. Those will be the three nodes. So if you take these three in a Y configuration and replace it, you end up with a delta. But that doesn't get rid of the other two resistors, which would stay there. So actually it does help, right? Because you could combine these two are in parallel now. These two are also in parallel. Then that would put these two guys in series and in parallel. Yeah, you could do it that way. Yeah, sure. That would work. At least it seems like that. It seems like that. Okay, so we have belt configurations. There's other ways we could do it as well. So let's redraw this. So we draw this circuit. Now what we're going to be doing is doing the transformation right here. That's what we're doing, the transformation. We could have picked the bottom triangle, or as you saw, we could pick the Y. So what we end up with is something that looks like this. All right. Okay, so what we've done is we've replaced, so this is still going to be node A. Node C is going to be all the way at the bottom of this. I don't want to do this a different way than we do when I did it in the notes. Look for Y to delta transformation. Okay, I'm doing the same thing. And then this is still node B over here. Okay, so what we've done is we've replaced that. Now what we're still going to have is these two branches going from B to D and C to D. So we have, and I didn't really draw this the best way. And this is D down here. So that's what the circuit looks like. Yeah, but what I'm going to do is I'm going to redraw it on the next picture because that's not. Okay, so quickly, what a better way to look at it would be. That looks a lot nicer. And so still we have the nodes A, B, C, and D. Okay, we know what a couple of these are from the beginning. This doesn't change. This is 9 kiloohms. And this is still 4 kiloohms. That's taken directly from the initial problem. And for this one, what we have to do is we have to define what we're going to call RA, RB, and RC. And then once we get those combos together, right, you can see that etc. So this whole thing kind of falls into line once you do that part. Okay, what we haven't done is we haven't calculated the values themselves. And so for that, I'm actually just going to rely on you guys with calculators. So calculate RA, RB, RC. I'm hoping that I don't have to, well, let me find the equations. So these are the equations that we have to use. Which way are we going? We're going from delta to y, which means that we're going to be using these three equations right here. And so RA will be equal to RCA, RAB over the value that we've called RABC delta, which was a combo of all three of those together. Okay. So what are the values of those? So looking at this right here, we can see that RCA was 12 kiloohms. We can see that RAB was 18 kiloohms. And then lastly, what would be the three of them add together? It would be 12 plus 18 plus 4. So what is that going to be? Well, I have it written up already. It's 6,000. Yeah, thanks. Okay, 6 kiloohms. And then RB and RC use similar equations. I'm just going to write the values up. Well, might just write the numbers. So RB and RC, that's going to be 18K times 6K over 36K, and that gives us 3,000 ohms. And then RC gives us is 12K times 6K over the denominator is always the same, and that gives us 2K. And then now, hopefully what we can do is just draw the simplified circuit right after that. I mean, we should be at the point now where we don't need to go through all the steps. So, what are these values? RA was 6,000, RB was 3,000, and RC was 2,000. So, what is it going to be? The final result is going to be 6,000 plus the parallel combination of, so these two together are 12, and these two together are 6. So 6,000 plus the parallel combination of 6,000 and 12.
How did you get RD?
Sorry, which one?
RD.
So RB is using,
Would it be 4 times 18?
we have to look back at the original. Yeah. I was trying to be quick and use the numbers that I had on the screen. You know, I think what happened was that in the beginning when I couldn't see the number, that was a 6. That's when I was having trouble seeing it. Okay. Yes. That's the main problem. This is a 6.
Okay.
Yeah. I was like squinting, but now that I see it, all right, good. So, so we draw the simplified circuit, and I'm just going to go ahead and boil that down to a single resistor. And so that resistor, R equivalent, is going to be equal to 6,000 ohm resistor, which I can call RA, plus the parallel combo of RB plus 9,000 in parallel with RC plus 4,000. Okay? So, I have the numerical answer. Does anyone want to try it in their calculator? I mean,
I'm not sure what you said there.
So I have 10K as the answer. I mean, does anybody need to see that worked out? Right. We know how to do parallel combos, so it would be this value times this value over this value plus this value, and then you would add the RA to it. Make sense? So these were helpful. And then you could also solve for the current flowing around this loop, right? The IS, which is what we were looking for in the beginning, is going to be equal to 12 volts divided by 10 kilo ohms, which gives us a value of, notice I never solved the problem finally. So 12 tenths, so 1.2 milliamps. So that would be the IS value. Let me make sure that might be 0.12. Maybe we just got through it. I think it's 0.12 actually. No, it is 1.2 milliamps. I was right. Okay, well it's 2, yeah, it's 12. Anyway, so regardless. So that's the answer. Okay, so we're close to the end here. What I'll do is I'll just flash the last example up on the screen. We'll take a look at it real quick, and then actually that'll be good because we'll be done with chapter 2. So we'll do that real quick. Okay, so the last problem, which I recommend you take a look at in the board notes or in the book. Example 2.28 asked us to solve for VO. You can see it's a single node pair with the exception of this. Well, it's a single node pair if you consider these two resistors to be a single chunk. And it's not anything that you haven't seen. I mean, the steps are pretty self-explanatory. You combine the equations together. It looks like there's no delta or y combos. Just the dependent source is kind of what throws you for a loop. I guess we hadn't done one with a current-dependent current source yet. So take a look at that. I don't think it's anything that's going to throw you for a loop. This last application example here, I wouldn't worry about it too much. It's not a very good example. That's the reason why I decided to do that. And that's it. So chapter 2 is done. And next time, we'll start on chapter 3 stuff. So you got your quiz dates, you got your homework due date, and we'll just keep chugging along next time. Please check your grades on Canvas periodically. Okay, just make sure if there is a discrepancy between what you think you should have and what you do have, I'd rather catch it now than catch it like in week 9 where I have a whole bunch of things that I got to straighten out. All right. Yes. Yeah. It wasn't a trick question. You know what? Tomorrow. Email me. I'll take a look at your quiz. No. That wasn't a textual trick question. So I see how some people. Yeah, it was, but I shouldn't have put that.
Oh no, you can do it.
Email me.
I just